Good morning, everybody. Welcome to the International Conference of the International Workshop of ERIES. It's a pleasure to have you all here. We will start with a brief welcome session with the President of LNEC, Laura Caldeira, and the coordinators of the project, Gian-Michele Calvi and Gerard O'Reilly. And then we will proceed with the scientific session. So I first give the word to Laura Caldeira, the President of LNEC. Thank you.
Thank you very much, Antonio. First of all, I will thank the presence of Gian-Michele Calvi and Gerard O'Reilly for being here with us and to be in this section. Thank you for this international workshop here in Lisbon. Good morning, distinguished guests, with colleagues and friends. It is both a great honor and a sincere pleasure to welcome you all to this important gathering. The evolution of earthquake engineering research in Europe began in the late 1950s, spearheaded by LNEC in Portugal and Júlio Ferri Borges, both theoretically and experimentally. Continuous experimental work took off in the 1960s with LNEC's applied dynamics unity and expanded it significantly in the 1970s with the creation of a uniaxial seismic platform. These uniaxial shaking tables support research on civil engineering structures like dams and help test sensitivity equipment and strong vibrations. Success and growing demand for more complex testing led to the development of a comprehensive seismic testing facility, one of Europe's more advanced. Completed in the mid-1990s, the facility includes both an uniaxial platform and a newly designed triaxial platform capable of testing large-scale models to failure, which you will have the opportunity to visit during your stay. The construction was partly funded by the EU under the SEISMIR project and national development plans. LNEC was responsible for all phases of design and construction, including the facility, the triaxial platform, and its control systems. Since 1995, the facility was hosted an extensive number of major experimental tests and has been recognized as a European large research facility. Over 3 decades, it was continuously evolved, responding to the user demands by upgrading hydraulic and control systems, nowadays with a modern digital control system developed by LNEC. Also, the fact that 3 reaction walls surrounding the triaxial shaking table allows for innovative test setups to be developed. Regarding European cooperative in RD&I projects, LNEC was participated in the numerous integrated projects with different European research networks and included strong components of research mobility between institutions. A consortium of earthquake engineering research facilities was established, with its core still represented in ERIES: LNEC, JRC, CEA, University of Bristol, and EU Centre. For about 10 years, the operation of the experimental facility was primarily funded through European programs such as ICM, TMR, IHP, and IHR, and social-economic knowledge base under the 4th and 5th framework programs of the European Union. The projects EcoEast and EcoLeader Lisbon funded by these programs, facilitated between 1997 and 2005, access to LNEC's seismic platform for groups of European researchers to conduct large-scale experimental studies in collaboration with LNEC, with full funding from UE. In parallel, LNEC was carried out tests as part of research projects in cooperation with other European research institutions. These were also co-financed by TMR and IIHP programs and the research mobility schemes, and by the RTRD program for the 4th and 50th framework programs. Under the EU 6 framework programs, the facility play a significant role in the integrated project loss risk mitigation for earthquakes and landslides, developed from 2004 to 2007 in collaboration with 45 European institutions led by Professor Calvit, that's here with us, EU Center and University of Pavia. While the projects were mostly related to experimental testing, pre-normative research for development of Eurocodes, development of materials, construction and strengthening methods, this project would deal with the other main field of LNEC's activity in this area: seismic hazard, vulnerability assessment, and risk. More recently, under the 7th Framework Program, LNEC participated in several large-scale research projects. Notably, it was involved in the experimental studies of integrated project ERIES, particularly in its component of transnational access similar to ERIES. Later, in the Horizon 2020 program, the core of the consortium teamed up with the seismology counterparts with EPUS and CIRA projects, where LNEC contributed to the development of European seismic hazard and risk models development, nowadays under the auspice of EFER, with LNEC's participation in its executive committee. This evolution led to the present Horizon Europe Research Project, ERIES, Engineer Research Infrastructures for European Synergies, given LNEC's several other activities in civil engineering, from wind tunneling testings to hydraulic, geotechnics, transportation, between others. It is only natural that ERIES expand its transnational access to wind and geotechnical engineer with the collaboration of new partners in Europe and Canada. These activities will most certainly contribute to a safer and more sustainable built environment, to build code developments, to new technologies for experimental testing, and for the construction of industry from numerical developments and other open access valuable test data. So, LNEC is very happy to welcome all participants in the 2025 ERIES International Workshop. Thank you for coming here.
Now it's better, huh? Okay, so the first reason is that when you are in this place, you are somehow breathing the history of earthquake engineering in Europe in the last 50 years or so. The first time I was here was in the second half of the 80s. It was the time when one of the most famous persons in earthquake engineering was Julio Ferri-Borge. It has been a great idea and a great thing to entitle to Julio Ferri-Borge the laboratory. Young people maybe do not know that he was the first chairman, actually one of the founders of the Joint Committee on Structural Safety, which was the body that essentially introduced in Europe, but I would say in the world, probability as a key issue in codes. All the codes that we have been dealing with probability or semi-probabilistic methods have been essentially finding their roots in the work of the Joint Committee of Structural Safety. And if you read what they were writing at that time in the 70s, you will find out that they were already conceiving a series of different protection to any possible undesired event, avoiding something through a different strategies. And this is something that has been somehow formalized in the successive years, but everything starts from there. In the late 80s, Lisbon and ELNEC in particular was at the core of this process. Then, in a few years later, in the 80s, let's say that the attention of research in earthquake engineering in Europe somehow moved to the subject of Eurocodes. And Eurocodes were not an easy process because, as you all know, in Europe there are many countries, and there is a need of finding sorts of, say, average response, or anyway, to compromise your pure scientific wish to the fact that the same code should apply in everywhere in countries that are very earthquake prone to countries where earthquakes are a secondary issue. This at the time has been a big bet, and many people in Europe not only in earthquake engineering, in other sciences related to, say, engineering or civil engineering, and also simply to decision-making or economics and so on, were wondering why to put such a big effort in the production of codes, that after all is something that has not anything directly to do with economics and so on. The first project in the series of projects in which ERIES is the last one was a project on pre-normative research in support of Eurocode 8, and it was started in '92. At that time, ELNEC was one of the key players. Another key players was the Laboratorio in ISPRA, the Joint Research Center of the European Community. The head of the area that was dealing with these issues was Jean Donéat, that many years ago moved back to his original country, Belgium. Anyway, I'm just reminding you about all these issues because of the third point. I have a second in the middle, but. Okay, let me go directly to the third, and I'll move back to the second. The third is that it is absolutely clear to me that all the story related to the Eurocodes has been a great success, has been a bet that has been won. Eurocodes are now by far the most used code all over the world, which means that they are a kind of a tool, an ambassador, a way through which Europe is more relevant in the world. So the Eurocode system has by far outlined the American codes. Of course, there are places where they still refer to the American codes, but there is no question to me that Eurocodes have won their battle. The fact that now we are close, essentially, we are in the process of adopting what is called to be the second generation of Eurocodes, is a big point. And I think that since, and now I'll move back to my second point, since now we are now at the end of the third year of this project, so we have one more year, and at the same time we are at the time when the Eurocode system is moving to the second generation. And second generation for the Eurocode system means 20 years. It does not mean 1 year. Because of all this necessity of moving slowly from one thing to another, is something that should be considered. And I think that this conference, I insist in calling it conference because it's, there are 100 people here that are expected to be in this meeting. So this is a conference, and this is a conference where most of the European large installations are represented. A few non-European are also represented. And I think that we should start thinking, and maybe in coffee breaks, lunch breaks, and maybe on Friday morning, what comes next. In 1 year, it will be too late. You do not start thinking what comes next when something is finished. You start when what is on is still going on. So this is not only a meeting at which we are recapitulating what has been done in these 3 years, and we discuss what are we going to do in the next year for this project. We should talk about future projects. For this reason, this meeting is very important, and it's nice that it is here at ELNEC in Lisbon. So the second point is the project, the one that I skipped to go to almost to what I was planning to say as a conclusion, and that is that this project has been a great success. We will discuss this in these 2 days, but I have not heard any complaint, significant complaint, from anybody or from any parties. And even European Commission clearly is quite happy with what, well, maybe it's too important to say the European Commission, let's say the European offices are very happy with what's going on with this project. We have been essentially using all the slots we had for experimental testing. We have been able to exchange a lot of researchers from institutions that are offering the access and institutions that are asking to access to large facilities. Most of the experimental research has been concluded. There is only something still going on, but most of this, the next year, will have to be used to transform the experimental research in papers, in publications, in conclusions, in something that will find its way to be used in the real world. So we have a project that has been a success. It's a project that is the last of a series that is lasting for about 30 years. It should not be finishing here. And for these 3 reasons, I'm very happy that we are all here and we start this conference. And I wish to thank you, our friends and colleagues from Lisbon, because they are always organizing a great event in this location. Thank you, Mrs. President, and thank you, Antonio, and everybody else here.
Okay, so I had some slides, but I guess I have to present just this one. I cannot move the presentation, but let's see if I can. Where is it? Okay, so here we are. So thank you all again for coming here this morning. So to get us started after the opening words of both the president and also from Professor Calvi, I thought just to give an overview of the project, of what it is we're doing here. Okay, so I think many of you know each other, at least the different communities, and what I wanted to give, and at least in this presentation, is to give an idea of what brings us all together, because I imagine you'll meet people you haven't met for the first time, and also maybe to try and explain what it is this project is. You've maybe taken part in it, but maybe trying to understand the bigger effort or the bigger idea of what's behind it is also something that can be quite useful to give better context to the next couple of days. So the overall objective, when someone talks about this ERIES project, is to provide this thing called transnational access, okay? And the idea of what the European Commission or the European Union is funding is to giving access to researchers, to research infrastructures, so laboratories essentially in our terminology, to conduct research that will advance the frontier knowledge in related to certain hazards, okay? So in this project, what we're looking at is seismic, wind, and also geotechnical. So we have a mix of different hazards, let's say, whereas maybe in the past we focused a bit more on seismic engineering because that's maybe where a lot of us have our background, but we're expanding into different fields that the European Commission is also eager to support. So the project is going on for a couple of years now. We're in the third year, just right exactly at the end of the third year, and we have one more, and hopefully we can try to translate these into some impacts as was mentioned just before. So given the difference and given the, let's say, the diversity of the different projects that we'll see over the next couple of days, it's kind of hard to present a big project to say to the European Commission, okay, we've got a lot of manpower, we've got a lot of great ideas, you just need to give us some funding, we've got a lot of tools in the laboratories that we can use and we can do some great stuff, but you kind of have to break that down and say, give a bigger picture to people who are maybe not very technical, okay? So the thing that we presented, we said, okay, we want to address these 3 different research goals. And most of you will know who are applying for the access as part of this project. We're asking you to try and let's say plug your project into one of these goals. And these goals were quite vague, but let's say everybody could get behind these, saying that, okay, we want to have loss-driven design and mitigation approaches, we want to have risk quantification and prioritization, and we also want to have green and sustainable development as part of our individual projects. That's something that not everybody has to do, but it's something we hope that people will strive to do in their work. And at the same time, the different areas we want to work on, okay? So we have things like the built environment, the things like critical infrastructures, and also industrial facilities and advanced technologies. So the idea that, okay, you may be working on risk quantification and prioritization as part of your work, but maybe it's just related to the built environment, maybe it's related to critical facilities, or maybe you're working on some new novel device that's a advanced technology, okay? So trying to break down the field of engineering into a more generic way that's communicable to a wider audience. And this relates to all of the hazards, all of the different areas that you're all working on. So let's say the seismic community, the wind community, and also the geotechnical community. Okay, so this is how we try to structure this project and present this as a proposal a couple of years ago. So the idea here, and this is what we were trying to get you to do in your proposals, was to say that, okay, this is the bigger map or the bigger picture of the project. Try and find where your own fits in. Maybe it fits in one of those boxes or many of those boxes, but at least it fits a bigger picture. And this is what's presentable and what's, let's say, communicable to people who are maybe non-technical, who are going to make some important decisions in the future. Okay, so I give a simple example here, but I think all of you could maybe find your own relative example on that slide yourselves. So to give an idea of who's involved, so we're obviously in Portugal right now. We're coming from different parts of the world. So these are the research infrastructures, or the laboratories, as we commonly refer to them. So these are who are involved as partners in the ERIES project. So you can see there's a distribution, people from all the way from Greece all the way to the UK, and also a partner from Canada in North America. So this is who's there, and yeah, this is exactly as I was mentioning before, partners in France as well, the University of Bristol, Western University in Canada, TUE in Eindhoven, the Universities of Patras and Thessaloniki, ESIS in North Macedonia, the University of Geneva, the Joint Research Centre in Ispra in Italy, and also EUS Pavia and EU Centre in both in Pavia in Italy. But this is who all of you are, okay? So if I flip back to the previous slide and I say, okay, this is all the partners where all the laboratories are located, who's part of the ERIES project, but this is a more real reflection of the ERIES project. This is reflecting where most of you are coming from, all the different institutes, your partners, all of your different people. If anybody finds your place is missing or something like that on this map, tell me and we can update it, okay? But the idea is to give a sense of community here, okay? And this is where everybody is located, but this is how we say, this is how everyone's working together, okay? So you can see it looks like a mess, but in a good way. And it's something that's very good to communicate to the European Union because it gives an idea of everyone's working together, okay? and also not together within Europe, but also you can see there are countries from outside of Europe involved there. So you also have the United States, Mexico, even Cuba, Oceania, Asia, and the Middle East as well are involved in some of these projects. So it gives a great idea of a lot of work is happening, but a lot of people are involved, and everyone's working together. So even from a non-technical perspective, it's a great initiative to support. So these are just some statistics, but I don't think this is really going to be of much interest, but it gives you an idea of, let's say, what was going on the last couple of years, and all of you are maybe part of these statistics, so thanks for taking part. So we had a lot of interest, a lot of, let's say, approval or rejection, and the acceptance rate of the projects was about 60%, okay? It maybe sounds like a bad thing that 40% of the projects were rejected, but really the purpose for that rejection was not that the projects weren't good enough. It was just we didn't have enough funds to do it. If we had infinite money, you could do all of the projects in the world and to do a lot more research. But to give you an idea, it's quite competitive, and there are quite a lot of you involved in this. In terms of the hazards and where people were focusing their efforts, okay, we can see over the different calls of proposals, there's a lot of different interest for the different communities. And let's say the balance of those, I think, is more of a reflection of the available facilities. I think we had more earthquake facilities than geotechnical and so on and so forth. In terms of the, let's say, research areas, you can see the built environment is a lot more popular, I think, because it's related to what we're doing every single day, like the place where we're sitting right now, where we slept last night, maybe where we're going for dinner later on today. This is all the built environment, so I think it's more common, but you can see there's a good interest across the different research areas that we were proposing. So when we come back to exactly what we said we were going to do, or what they asked us to do in the call we applied to a couple of years ago, what they were looking for is they wanted wider, simplified, and more efficient access to the best research infrastructures available to researchers, okay? So the idea that maybe there's a great facility here, but you're working somewhere else that doesn't have a facility, that shouldn't preclude you from being able to do good research. So they're trying to fund that and make this whole transnational access possible. So this idea of curiosity-driven research, this is what we're trying to achieve. Breakthrough leading-edge research to enable all of this to happen and to make it available to the wider community. This is what they're trying to focus on. Also to harmonize and have a broader, let's say, exploitation of the synergies across Europe is something that they're interested in. So you can see on the map on the previous slides, I think we're achieving that. Everybody's working quite well together. And also a new generation of researchers. So the idea that a lot of young researchers are coming up through the ranks and are involved in a lot of these projects. I think I have some stats in some other slides that I can show another time. And it's one of the reasons why we have this Young Researcher Award, which we'll talk about later on today and tomorrow. But to have a new generation basically trained and that can exploit all these new tools and all these new infrastructures to conduct the research. And also the cross-disciplinary fertilization. So the idea of the different communities are coming together now, and this is, I think we've achieved this as well with this project. Something as well I think we'll talk about tomorrow morning is that the world is becoming more digital. The idea of having all your data on hard drives and in your desk, on your drawer is let's say, a thought of the past. So something that the European Commission is very interested in doing is everything is digital, online, cloud, things like that. So we need to, let's say, make that transition as well. So that's something that needs to be a core part of the project and something we're trying to do as well as part of this. So I think I'll close with this. So overall, we have 69 user projects. So we can see there's a lot of impact around that. Over 400 researchers involved. I think there are about 100 of you here today, so it's only about a quarter of the project, the actual involvement in the project. 47% of these are early stage researchers, so almost half of those people are young researchers, so it's a really good involvement. 38 countries from around the world involved in that, but also 56 nationalities. So we have a lot of, let's say, diversity. People, I myself are from Ireland, but I'm working in Italy, and I think many of you can find yourselves in similar situations. You're moving around the world, and there's a lot of, let's say, cultural exchange from that perspective. We have 128 research institutes or organizations involved, so a lot of, let's say, distribution among different players, and also 45 industrial partners. So let's say a good connection with industry as well, because while research is nice, you also need to try and make an impact with the industry as well. So to give an idea of the next 2 days, so here we are today, we're currently closing the first session. So we have a couple of sessions today. I've tried to divide them up into, let's say, the themes. So we have wind engineering will come first. Well, first we have some general session. We have 2 presentations before the coffee break. We'll have a wind engineering session always in this room, and then we'll have some parallel sessions. So one thing I just wanted to note is that on the program you'll see small auditorium. Just ignore the word small. It's actually going to be in here. Okay, so we just have 2 rooms basically. We have the auditorium, and I think room 6, which is around the corner, you can see as well. Okay. Tonight we'll have the social dinner. It's in a place called Espacio Tejo, I think you say it, but we've put a QR code for the Google location on, so you can find it on your phones. Tomorrow we'll have a working session in the morning, even though I think I mentioned this in an email to everybody. Maybe it doesn't sound like the most glamorous thing, but that idea of data, policy, impact, future, that stuff is more important than you think, and we'll have an interactive session where we'll have QR codes and, let's say, responding on your phones to kind of get your impression and get your feedback to how we can do better, maybe how we can shape the future for projects like this. We'll have some more sessions, and then we'll have the closing address, and that should conclude the technical sessions of the first few days. On Friday, we have a lot of internal meetings, let's say the organizational stuff, which I'll try not to bore you with, and also to give you an opportunity to take a look around the city as well, okay? So I think that's it from me. So thank you very much. I guess there will not be any questions, so I think we can proceed to the next presentations. If I'm not mistaken, we will have a presentation from Professor Guillermo Bitz-Saumlag. He's coming all the way from Canada, and he's going to give us a presentation on the non-synoptic loads of wind loading. Okay.
Mihaele, Gerard, and Maria Pia introduced the vision of this project. It was very interesting then, and we had wonderful couple of years, you know. Yesterday I was in the court committee. I literally arrived in Lisbon this morning, and if there's a jet lag effect, please excuse me. Okay. Today I'll be focusing on non-stationary wind loading on structures. In wind engineering, most of the codification and the experience was focusing on synoptic wind, large wind system that are typically called straight wind, you know. But in this ERIES project, many of the projects were focusing on non-stationary, non-synoptic wind. And of course, there are few synoptic wind for special structures as well. I'm going to present tornadic type of wind loading and downburst type of wind loading and synoptic loading on special structures. It fits into what Gerard was presenting. Primarily, we look into critical infrastructure and design them for wind risk. You know, in wind engineering, our processes are front heavy. You know, majority of our effort is in evaluating wind load. You know, you have the hazard estimate. After you quantify what kind of wind system, what type of wind system is happening, a big chunk of wind engineering is how that wind system interacts with that specific structure and produces the load, you know. And majority of our research focuses on this aspect of the research. We used almost for all ERIES project the WindE dome facility. It's a hexagonal facility, large-scale facility. It is like the size of this auditorium. And imagine if you have a fan on all walls and on the ceiling, you know. And by combining different fans, we can produce different kind of wind system. And we could do multi-scale testing, whether it is scaled down solar panel or full scale solar panel or scaled down long span bridge and things like that, And it's a 3-layer system, it's 3 floor. The first floor is a model shop where we make the model, and this hall that you see here is a turntable and a lift. It goes down to the model shop and we make our model and install it. Then we lock it on a testing position. In wind testing facilities, wind direction is important, and we don't change the direction of the wind, but we rotate the study building to mimic that effect, and that's why we need the turntable. And the upper chamber is like a 100-ton system hanging from a ceiling, and you have 6 massive fans, each one of them the size of the door, Either they can suck the wind or push the wind, Imagine if you have fans on the wall and you fire them in oblique wind direction, it produces circulating wind. And if you suck it from using the upper strong fans, that's what produces tornado. For downburst, the reverse is happening. Just to give you some perspective, for straight wind generation, we have one wall that has 60 fans with 1 meter diameter and with active grid and passive. Okay. And as in typical wind tunnel, by the way, our wind tunnels for wind engineering application, they are different from aerospace by the way we generate turbulence. We deal with the most chaotic flow out there, so we have passive system like ground roughness or some active turbulence generation system and things like that. Just to give you a perspective how we do the test, this is a building getting ready for a downburst testing. We have pressure taps that we connect, and they are simple pressure tube. As you puff through them on the surface of the building, at the back end you have pressure transducer, and it picks the pressure difference. That's how and when you integrate the pressure, you get the loading. This is a typical downburst testing on that particular building. To visualize wind, you have to put something in the tunnel, otherwise wind is invisible. We use staging smoke that artists use to visualize it. It's a tornado simulation. Yes. I will start to distinguish the 3 different wind systems. In typical synoptic ABL, what you see is a wind flow affected by the ground. Close to the ground, it is 0. Depending on the roughness, the chaoticness, the turbulence could be high. For example, wind in Lisbon could be more chaotic. When you go to the countryside, that green chaotic, the turbulence will reduce, And when you have this type of wind interacting with a bluff body, it has a signature aerodynamic distribution, pressure distribution. Of course, that distribution is dependent on the shape of the building, but this derives majority of the bluff body characteristics. When you look at downburst, basically, you have a jet coming from the sky and hitting the ground and laterally expanding. Strictly speaking, it's like a donut type of vortex descending down, and when it hits the ground, laterally expand. And when it is far from the center, it develops into something that looks like boundary layer, but it evolves from a downflow to strong horizontal flow with maximum velocity near the ground, and that's what makes it problematic. You have the maximum velocity where most of our civil infrastructure are installed. Actually, from a North American context, 60% of the wind-induced damage are related to this kind of what we call local system. It could be downburst or tornado. It's only the coastal region that are dominated by this type of ABL flow, So we need to really mimic, following the Allen Davenport load chain, we need to characterize the wind. Then you have to model the interaction of this unique wind system with the structure. It is only at that stage you will be able to produce useful design information. And depending on where the building is located, in relation to those radial direction, how the building is oriented, the load could be different. And we look into all these parameters. When you deal with tornado, it is even more complex. It's a three-dimensional vortex type of flow. Yes, hurricanes are also like tornado, but hurricane is almost the size of Texas or maybe Europe, Then any building in front of those kind of massive system, it doesn't feel the rotation, It comes as only a wind direction, and we treat it as a straight wind. But when you look at tornado, they are the size of the order of a building, They range from maybe 50 meter, 100 meter, to a couple of kilometers. So that in the order of the building. Then that three-dimensionality of the flow will impact the load distribution, and we need to capture that, Then how do we characterize it? It is a rotating updraft characterized by a significant drop in the pressure, atmospheric pressure. That's what this variation show. Then when you look at the velocity distribution, it is three-dimensional. There is a radial flow, there is a tangential flow, perhaps the strongest, and there is updraft. There are three components, and we need to capture. If we pay attention to how the strongest velocity component, which is the tangential velocity, varies with height, it follows this distribution, Again, like downburst, close to the ground, it produces significant velocity. That's why we are interested in tornado. And compare when you see the variation radially, it starts from zero, it peaks at a radius called core radius and gradually dissipates, So it is this type of wind system that we are trying to produce, and the interaction of this wind system with whatever structure we have. Then this is also translating, To this you have the translation. Then since it is a very small system, then whether if that tornado is passing on the building, how far it is from the building, how big is it compared to the building, all these are parameters that we have to deal with to assess the wind load, So having provided the theoretical background, I will jump into some of the projects we have been working. Perhaps another visualization of the flow for tornado. When you zoom in into the structure of the tornado, there is an inflow this way. Okay, I have. This region is the inflow region, and it goes up, and depending on the swell ratio and the structure, there is a downdraft. This is just at the touchdown, So you have this kind of flow structure in a tornado. What makes this very difficult during the experiment is the measurement of the wind field by itself is a big challenge. I know most of you who spend time in the wind tunnel, we use like Cobra probe or hot wire or anemometer and things like that. Majority of those measurements are directional. In straight wind, we know where the wind is coming and we orient it and we measure. But with this kind of system, it's three-dimensional and it's very difficult to measure with those kind of traditional techniques. So what we did was we developed not the PIV system. We modified the PIV system to work on large scale. We use again the staging smoke as a seeding, and we fill the room with those kind of seeding, and we use this kind of laser light, and underneath the turntable, this is a glass. underneath the turntable, you have this kind of cameras, and by monitoring the particle movement, we can measure the velocity. And that's how we characterize the tornadic wind flow. Now, this particular tornado is moving from left to the right, and you can see those peak tangential velocities at the core center, and it gradually dies out. And here you have a transverse and trackwise direction. These are the velocity components, and the dark one is the vector sum of these two, the horizontal component. And as you can see, tornado wind flow is non-stationary. In synoptic wind, at least you have an average mean. I brought two projects. One is the ERIES TNG, tornado near ground measurement with University of Birmingham and some universities in US, and ERIES Solar was 3 universities in Europe, Zagreb University, the Von Karman Institute, and Felix here, La Corona University, right? Yeah, 3 of them. We did both straight wind, tornado, downburst, and Bora wind, you know. I learned Bora from Horvier. I never knew there was a wind called Bora, you know. And he has a field measurement. He came and we were able to reproduce it, you know. Actually, when we did this, this was the first time that a tornado and a downburst test was carried out on solar arrays, you know. Basically, for tornado study, in addition to the building, we put pressure tap on the ground as well, you know. That's what these engineers are doing, you know. When you flip the floor, you could see the tubes. I did animation of the tornado using NVIDIA Omniverse. As you see, the tornado is migrating at a distance, a radius of maximum wind velocity. And when it hits the building, you see this kind of pressure distribution. And I have another simulation. This time, the tornado is passing, if the video works. It's passing through the building. By the way, there is no codification in Eurocode. For example, Mihaly was talking about that. ASCE developed a tornado provision, but primarily based on synoptic wind, not tornadic wind experiment, but synoptic and some engineering judgment, you know. So with this kind of data, we'll improve those kind of provisions. And as we speak, actually, this is encouraging us to establish a codification as part of the National Building Code of Canada. I know Mark Sterling and his team and many in this room will be maybe in the future working to make it part of the Eurocode. You know, what's interesting about this project, personally, it made us work. You know, we had 8 projects. We finished 5 of them. We are working with Professor Riccadelli, the 6th one now, and during this time, we worked with 10 different universities, and we expect to work with 6 more. And the kind of experience exchange that's happening, you know, the inspiration we get from our visitors and the inspiration our students get from all this kind of collaboration, it is immeasurable. You know, it is, it's one of the last 2 years, actually, it was a blast for us, you know. When you look into the pressure distribution on the ground, that's what you see. We have this stationary tornado and translating tornado. The translating tornado produces a very clean pressure distribution. As you can see, the pressure drop is clearly captured here. You know, when you have wandering and movement and stationary tornado, you will see this type of events repeating, you know. So when you have this kind of non-stationary data, you have to go back to the drawing board. You know, all your peak calculation, the way you understand CP and everything have to be revisited once again. You know, can you imagine when the tornado wanders and when you do tornado simulation at the wind E, when you repeat the tornado, it will never pass on the same path. It will shift. You know, so we interpret it as a change in angle of attack. You know, like usually a different location of tornado would mean either vertically or horizontally it will attack the building in a slightly different angle, you know. So by repeating those, and we cannot treat them as a simple one physical system and the variation is stochastic variation. It is physically two different events, you know. So what we are doing to get a representative peak value is like if you take these two tabs, this is for different repeat. This is the time history of the pressure, and you have this kind of variation, you know, then when you repeat the test. So we are enveloping, and the envelope is representing the peak. Okay. When I see Gerard coming, I think I have to rush, you know. Then I will go to the second project. This is the ERIES Soral project. As you can see from the time history, this would be a synoptic wind field representation. The tornado would look like something like this, you know. That's why we call it, it's obviously non-stationary, you know. Just for visual comparison, this is a tornado load on the solar array, and this is a straight wind load, you know. So in this way, we can literally design in the future, you know, when you see this big solar farms, you know, they are sprawling in tornado-prone areas or downburst-prone areas, and we need to design for those kind of wind system, and I think this ERIES projects are helping us to do that. There was also another interesting part to this project led by the von Karman Institute of Technology. They are putting anemometer on drones and try to characterize the wind field in this type of problematic wind field. You know, we did this kind of experiment as well. And I encourage you to attend, you know, Felix, Harvey. I didn't see the von Karman group. Perhaps they are here. Please attend for more details, you know. We also did a downburst testing on communication tower with Bucharest team. And Anne-Catherine, I saw her there, you know. Technical University of Munich, they are experts in form-finding membranes, you know. Unfortunately, for this kind of structures, there is no codification, there is no wind load provision, you know. So Anne-Catherine came with 5 or 6 different type of shape, and we did downburst, tornado, but primarily synoptic type of loading on this kind of unique structures. And the last project that we just recently completed was AeroBurst project, where we looked into the impact of downburst loading on long span bridge section with NTUT from Norway. This team is monitoring a long span bridge, and they observed 5-meter deflection because of this kind of local wind system. That was the inspiration for them to come and do the testing. And I can tell you, this is the last slide, by the way. I can tell you, each one of the group is involved in codification group. For example, for the last project, now as part of the International Wind Engineering Association, many of you, I know you are part of that, we just created non-stationary loading on large civil infrastructure committee, just a precursor to codification. With that, I will stop my presentation. Thank you for your attention. If there are any questions.
Thank you, Girma. It was a really interesting presentation, I must say. In the interest of time, I don't think we have any moment for question, but we'll go to the coffee break afterwards. So I guess we can chat then. So thank you once again to Girma, and we will go straight to the next presentation. So it will be Professor Anastasios Textos from the University of Bristol, and he will give an overview of the activities that are going out there at Bristol. Okay.
So thank you very much, Gerald, and congratulations for all the excellent organization of this project. It's always a great pleasure to come to Portugal and to Lisbon to see good colleagues and friends. So first, let me acknowledge the contribution of our partners and colleagues from Bristol. It's a long list, obviously, and also there is an even longer list from the user groups, about 50 people. So instead of listing them in the first page, you will see their names later on in the respective projects. The new laboratory at the University of Bristol was started being constructed in 2018. It's a 15 million euros investment. Everything seemed to be going pretty well until multiple hazards like Brexit and the pandemic made the construction more complex. But at the end, I think this is the installation that we're offering to ERIES, and it is quite complementary and versatile, as you're going to see. There are three main entities in this laboratory. The one is the shaking table, sometimes equipped with a shear stack to be able to test, let's say, soil structure interaction problems with bottom-up excitation. And this is a 6x4 shaking table. It's a 50-ton table going up to 2 Obviously, there are many other tables in the world right now that have similar size. Needless to say, an order of magnitude larger shaking tables in Asia, so there's no comparison with what we can see in China and in Japan, in fairness. But it fits the purpose for the research that we do. And I think sometimes it's not just the size, it's also the way that you devise the problem you're going to study, and like Gerald nicely said, to do something that is curiosity-driven, because this is essentially what is driving research and novelty, and obviously without underestimating the size of the problem. But talking about the size, this is the small mini monster, if you like, which is 1.2 by 1.2 meters area, a small hexapod shaking table at the University of Bristol again, which goes up to 10 G. So this gives the diversity I was talking about, that is facilitating test of equipment or applying large accelerations at a higher floor and the like. And then, of course, the soil pit, which is something that diversifies this laboratory quite substantially. There is another very large soil pit in Germany, Hanover, if you're aware, by Fraunhofer. That's mostly on offshore wind turbines. Us, it's a little bit different, it's smaller. It is something that you can fill with sand, particularly clay would be harder. But essentially, you can apply loads either laterally for the case of a bridge abutment or for the case of a retaining wall, or you can apply loads from top to bottom for a wind turbine, onshore or offshore, or for a buried pipeline, for various types of projects. And this is pretty much how it looks like when you do tests in the soil pit. So these were the installations that were offered in the framework of ERIES. And it looks very simple to empty the pit and fill the pit with vacuums and with shovels and all that pieces of equipment. But I can tell you that it takes quite some time to do this, and also to compact it properly and measure it properly and do all the job as needed. But it's kind of a smart pit in that it has fiber optics and load cells all around, accelerometers, buried other measuring devices. And this gives a very well-controlled estimate of the performance of soil structure interacting systems. Now, going to the individual projects that we served during the ERIES period, I have to say that we have, because Luigi just asked me previously, how many projects have you completed? And the answer was 1.5, which means one, this is the one that Professor George Milanakis is going to talk to you tomorrow morning, so I'm not going to spoil it, just give you the overview. And the others are ready to be tested this summer and this fall. The reason is that, as you're going to see, they're very multidisciplinary and quite complex. All projects, obviously, are complex. But I think these particular ones required a lot of design to de-risk. And this, as you know very well, takes quite some time. So for the Scar and Shake project in particular, which is led by Politecnico Milano, Maria Pina Limoncelli, and also by our colleague Dimitris Karamitros in Bristol, just to say that we thought it's a good practice for every different project to allocate it to a different colleague to run it and manage it, because it's impossible all this to be done with few people. So you'll be seeing a name from the Bristol side in each specific project. So Dimitris was the coordinator for this one. And like I said, some groups are quite long, so I'm not going to name them one by one, but you can see that was great contribution by various entities. So the idea here is effectively how scour can affect or undermine the seismic capacity of bridges. This is to cut the long story short. Now, this is a test that, like I said, I'm not going to get into the mechanics at all, because George is going to present this tomorrow in detail, but essentially it's a test that looks pretty simple, if you like. It's the shear stack with some single degree of freedom systems and a scour that is mechanically excavated, let us say. And that's the instrumentation, which looks straightforward. But as George is going to tell you tomorrow, it looks simple, but it's not simple at all. To be meaningful, to scale it properly, and to learn something that we don't already know. So, as I promised, I'm not going to spoil George. You're going to do that tomorrow. And also, you're going to talk about remedial measures and what we can do, perhaps, to mitigate this effect and improve, or let's say, drive the scour soil structure double interaction in our favor. So this is the purpose of this specific project. The other project, which is also something we find quite interesting, with the user group led by Camillo Nuti, with non-EU advisor from Abu Dhabi, Professor Andreas Kapos. This is coordinated by our colleague and friend, Professor Flavia De Luca, and a list of people who have great contribution in this project. So this is pretty much about what happens when a bridge deck exhausts the seismic gap and goes with, creates impact on the backwall. This is quite a complex problem. As you know, in the codes, there are many, many things that we don't actually address in this problem. That's for the reasons of complexity on what's happening behind the wall in particular. So the idea was to generate a system that will create this large-scale test to be able to learn some things that we don't know. For example, what is the duration of pounding? What is the constitution of restitution? How does the constitution of restitution change because of multiple closings of the gap and multiple impacts? And what is the rotational stiffness, the dynamic rotational stiffness of this footing? Because I can tell you in advance that the more the footing rotates because of soil structure interaction, the whole mass that is activated behind the wall has a different shape and a different volume. So we're talking about a pounding problem with mass 1 of the deck and mass 2 of the backfill. Mass 2 is the greatest unknown of the problem. And this depends on the supporting conditions. This is something you can only effectively experimentally identify, because numerically this is your input. So this was one of the important things to try to capture in this problem. But there are also challenges. One, to be able to instrument this problem properly, because all this impact happens very, very quickly. And you have to be able to capture this pounding, and also to make it realistic enough, scale in terms of momentum ideally, and be able to extrapolate the results. You can see here our modular design of the stem wall and the back wall, and we have several different types of abutments mimicking, if you like, the kind of continuous stem wall back wall system that we've got in Europe, or in contrast, the Caltrans-based system where the back wall at the top is sacrificial, it's just sheared off after pounding, so the mass that is activated is just very superficial. So between these two extremes, we thought essentially and initially, let us have a large mass, drive the actuator, and just throw the mass and see what happens. But you would never do such a problem, solve this problem like this, because obviously there are going to be some rebouncing of the mass against your expensive actuator. Then it will be hard to repeat the test. So everybody who is dealing with experimental mechanics, they know that this would be something to avoid. So that looks very nice to create a sketch, but essentially that's not what we decided to do. We thought it's better to just use gravity in a very well-controlled way, minimizing the eccentricity, have a hanging mass that we can calculate like 20 centimeters from the top, mimic the momentum that we're going to get, and create a pounding like this. And this is what we are actually designed to do. And all the design has been completed, footprints to the maximum detail. There are many, many questions, by the way. What should be the material that we're going to use at the impact point? How are we going to distribute the force so that we make it an equivalent pressure? How are we going to measure the constitution, the coefficient of restitution, and all the other challenging aspects? And also, okay, obviously we need to do numerical wall to de-risk, but effectively there are some practical problems we have to address. You can already imagine that the soil pit is small. So effectively there are going to be some reflections at the boundary of the wall that will be interfering with the things that we'll be measuring. So we had to design everything very, very carefully, identifying all the parameters, the tangential friction, the properties of impact, the duration of impact, numerically, the effect of the boundary walls, practically to assess in advance how much time do we have? What is the time window that we can use that is not subject to the interference of the reflecting and the superimposing waves from the boundary? This is small, but it's large enough to be able to study the things that we want to study. But this is just an evidence of all the work that has to be done to de-risk such a test. And you can see here how like I mentioned previously, the participating mass changes because of the rotational conditions at the end, if you like, the stiffness, the dynamic stiffness of the soil structure interaction system. That's quite interesting, because when we're designing bridges and we want to identify a spring or a dashboard at the end of the abutment, somehow we need to calculate how much this mass is. And that's something we basically don't know. Now, going to something very, very different, this is a third kind of test. This is the half that I said. We did 50%. It's a 3D printed unit. In this case, it is led by the University of Porto, Professor Umberto Varum, and from the side of Bristol, it is led by Professor Raffaele De Risi, and a list of good colleagues that have contributed in this project. And effectively, it is about what is the strength of buildings that we 3D print. We know that we can 3D print them, but are they suitable for seismic regions? So there is an excellent cooperation with the University of Porto in this case. These are some examples of 3D printed units around the world. I don't know if you would really like to live in these places, these units, but they can be printed pretty easily. So these are the properties that had to be identified. Many, many things to take into account. Effectively, it's also the speed that the nozzle is moving. It's the quality of the concrete, whether it changes the strength by height, what is the different properties in plane and out of plane, what is the property of the void. And this is the 3D printer that this industrial partner, HTL, introduced in the project. These guys, these are an Irish company. They have been quite keen in printing the unit that you can see on the right. This is the 3D footprint of the test that we're going to do. Effectively, we have 3D printed it. That's the 50%. And we're waiting for 1 month for the concrete to cast. to test it early June. And these guys are quite keen, like I said, to print, so they have even printed their own headquarters, which looks like what you see in the picture on the right. And then before doing the printing for us, there was an extensive work done at the University of Porto identifying the properties, the material properties. Why? Because somehow we had to know what is the material properties and the sectional behavior before we design the 3D printed unit to make sure that we will be able to damage it. Because we also have some limited capacity. We can test up to 50 tons, up to 2G, that's it. So if we couldn't reach the level, the threshold of damage, it's a pointless test. We're just going to have a rigid block moving. So that's why this component testing involving compressive strength test, diagonal test, panel tests, 4-point bending tests, and all the like, a lot of numerical analysis, a lot of prediction. Credit goes here to Raffaele De Risi, who did the vast majority of the work, Tansu Kokce, who did fantastic work. They even parameterized with the aid of ASDA. You can see here how the design was parameterized with a fantastic tool that Raffaele built in practically playing with the different properties. Shall we introduce more openings? Shall we introduce more mass? Both of them would create more damage, obviously. And what's the sweet spot, if you like, between something that is realistic enough and at the same time we can break it, to put it like this. So this is the final drawing and the different footprints from the top, cross-sections, expected damage running obviously Kahramanmaraş earthquake sequence. That would be the easy choice, but obviously we cannot really overshoot. This is going to be an incremental dynamic analysis test at the end of the day, starting small, doing everything elastically, and then upscaling little by little. That's the final footprint with a mass that you can see on top, currently 3.6 tons, maybe we increase it a little bit. And this is the casting of the footings of the printer. Something important that I didn't mention, the 3D printer effectively was transported to the lab, was rested outside the shaking table and printed on site. So we didn't have to, kind of elevate or carry with a crane the whole thing. And this is the time lapse of the 3D printing of this unit. And I can tell you it's not as simple as it looks, because there are many things, and even in bringing and testing the concrete on site and during construction and the like. But the good news is that the whole thing is there, printed, waiting to be casted, and more news next month, effectively, or in our next meeting. It was a very interesting experience. I think overall, in retrospect, that's all very feasible and promising, but have to be tailored very carefully, because we're talking about structural properties. It's not just about in earthquake regions, at least. And finally, there is this fourth project called Hysteresis. This is led by Professor Isan Bal, with the aid of great contributors from other places. I would name just for this purpose Solomon Tesfamarian from Canada, and our friend Osan Kwon, also from University of Toronto. Also Roberto Tomasi from the Norwegian University of Life Science, because that's actually a kind of a very different project. Isan is going to tell you more tomorrow, so I'm not going to say too much. Just a little bit about the motivation, because administratively wise, this is kind of linking two work packages. That's work package 9, whatever Bristol delivers, and work package 15, which was by design combining promoting the collaboration between different laboratories, that being the University of Patras. So this test is co-led by Bristol and Patras, and initially the question that was put forward in the proposal stage to the Commission was actually, okay, can we really do real-time hybrid testing in a single site? Yes, we can offer that. Can we do real-time hybrid testing in multiple sites? Probably not as real time, maybe nearly real with the problems of latency, but pseudodynamic testing we can definitely do in a single site or many sites. And this is how this has been designed to test something that looks conceptually what the UC San Diego has tested recently. That's a fantastic test of a 10-story timber building in the US. Our test is conceptually different in that A, it's substructured, So the argument is you don't have to go that big. You can definitely solve something faster. And secondly, we can account for soil-structure interaction. So without spoiling too much, and also because I got the message for Gerald sitting in his presidential chair, this is the finalized version of the building we'll be testing. This is the envisaged hold-down system that is going to introduce a hierarchy of failure between plasticity of the soil, a little bit of uplift of the foundation, a little bit of yielding of the hold-down mechanism, and also assuming that the panel that you see here will remain elastic, the introduction of a damper as an extra connector, if you like, as a bracing system as part of this substructuring process. And this is my last slide, practically showing, as Isan is going to show you tomorrow, how this is split A between countries. So in Bristol, it's going to be the foundation that will be tested, including the soil, the slab, and the hold down in smaller scale. The energy dissipator, this is a sand damper in Patras, physically tested, and all the rest substructure and tested numerically in Toronto and in Hansa University of Applied Sciences. That's how the footprint looked like. This is a test that will take place later this year, definitely before next March, because otherwise I think we'll be in trouble. And this is pretty much how the substructuring looks like. So with that, thank you very much for your attention.
Thank you very much, Tassos. Again, I think we are almost 20 minutes behind time, so I think we'll go straight to the coffee break, which should be out that door somewhere, and we'll meet again at 11:45 in this room again, okay? Thank you again.